All right, continue on here. The rain has settled down a little bit. There was kind of a severe storm that passed through there before the last video ended. We knocked over our trash can, but anyway, everything's okay, I think. So continue on here. Special relativity. What's the story there? Well, you can construct an inertial frame by arranging clocks and rigid rods in principle, all right? Then, well, that's no longer possible in GR because gravity interferes with the construction of the inertial frame. So the best you can hope for is the construction of local coordinates tied to the idea of what we call locally inertial frames. So locally inertial frames follow the motion of individual freely falling particles in a small enough region of space-time. All right, that's how you set them up, something like that, I guess. Now, one of the casualties of this way of thinking is that relative velocity of faraway objects will no longer be meaningful because you won't be able to compare two faraway objects with the same frame of reference necessarily. All right. So, all of this leads us to suggest that we should think of space-time as a differentiable manifold. And I'll just assume that the manifold's smooth, meaning that the functions that we study on it have as many derivatives as you want. I'm not going to fuss over once or twice differentiable versus thrice differentiable or many times differentiable, any of that. But anyway, and again, the curvature of the manifold is what gives gravitational physics. That's where we're going. We're not there yet, all right? And so he does give a nice concrete sort of physical discussion here of the how the Einstein's equivalence principle implies gravitational redshift. Basically, it looks at explains that the change in the wavelength divided by lambda naught should be something like the acceleration due to gravity times z divided by c squared, and that's also equal to the change in the gravitational field over this. So you have wavelengths which are redshifted as they go from here to here, let's say, and so if you study that and you sort through the paragraph that Carroll writes about it, he explains that basically means that you can perceive it as the clock on the tower appears to run more quickly. So yeah. So there's we're familiar with time dilation in special relativity for things moving fast, but this is a new thing. This is a time speeding up in the presence of gravity like that. Okay, anyway, so being a little bit vague here, and that's intentional. So that's a quick run through of the equivalence principle. Basically, if we think about the equivalence principle carefully, we will be led to the concept of local frames of reference, right? The impossibility of using a global frame of reference, and as such, that leads us naturally to think about studying. Let me take my other pages over here. That leads us to study, perhaps, it leads us to consider local frames of reference as opposed to global ones, and as such, the manifold is a good mathematical object to capture that idea. So here we go. So a manifold is it's a set together with these coordinate charts, all right? And I mean, if you want to read more about how to define manifolds carefully, I recommend, there's John Lee. It's a good author to read about these things. if you read John Lee's books, they're really helpful. For background. And so he has a whole book, I think, that's pretty much just devoted to more or less fussing about the topology on manifolds. And so really, I think we need it to be second countable Hausdorff space, something like that, whatever that means. So there is some backstory here. I mean, it really shouldn't just be any set. It should be a set which has, nice enough topological properties. But we don't require much. Well, I guess that depends on your perspective. But it certainly comes equipped with coordinate charts, this manifold does. Coordinate charts are one-to-one bijections from the manifold down to Rn, all right? And we also insist that the coordinate charts go to the same value of n throughout the manifold. Like, you can't have a manifold that's somewhere two-dimensional and somewhere else three-dimensional. That's no allowed, not allowed. And these are bijections from open subsets of the manifold to their image in Rn. And in particular, we require that this transition function, if you will, so here, if we follow the map, we go the first shall come last, right? So we do y inverse comes up to here, and then x to come back down. So that's a mapping from Rn to Rn. And if you study advanced calculus, to say that a mapping smooth from Rn to Rn, we can make that rigorous. And one of the theorems which comes from that is just that is achieved if the Jacobian matrix of this mapping is full of smooth partial derivatives. All right. So then these two charts are said to be compatible if they don't overlap at all, which is not my picture. All right. Or scooch this up a bit here, or if their transition function, let's say, is a smooth map on Rn. All right. And so definition: if we have a set for which the domains of the charts cover M, and we have this set of charts, all right, which we'll call A, a family of compatible charts, then we call A an atlas for M, and the set M paired with an atlas is what we call a manifold, all right? And you can do more. It's sometimes interesting to talk about taking a given atlas and adjoining all possible compatible charts, and so to obtain a maximal atlas. And if you have a set paired with a maximal atlas, that gives you what's called a differentiable structure. All right, so for a given set, there may exist more than one such structure, but not always. Sometimes there's just one. I don't know. Actually, I'm not an expert on that. I'm not sure. I know that there's more than one differentiable structure, at least in a few cases. Let's see here. So let's move along. Page 5 here. So I am going to spend the next little while here just running through. I don't have papers are getting it's so wet out here. I'm afraid I'm gonna the paper's gonna get smudged or something here. Let's see. Okay, so the next little while I'm going to run through how do we do calculus on a manifold, what are we interested in. So it's really just a lightning fast review of these things. To start with, you want to talk about what does it mean for a function from one manifold to another to be smooth at a point. What that means is that there exists charts x and y such that the local coordinate representative is itself smooth. So this function down here is a function from Rm to Rn, and smoothness of that function, again, can be judged by smoothness of partial derivatives of the Jacobian matrix. That's a reasonable way to think about it, all right? So the local coordinate representative of f, I called it big F, from Rm to Rn is smooth if this Jacobian matrix is a matrix of smooth functions from, each one of the component functions here. This is the column, so the component, so each one of these guys has, let's count it, it has n as in nanu, n component functions. Each one of those is itself a function from Rm to R. Those guys, these partial derivatives, have to be smooth functions. There are m times n of those. This is a n by m matrix. All right. Anyway, that's what we mean for smoothness. We judge smoothness of the function from one manifold to another in terms of the smoothness of its local coordinate representative. In other words, the way we do calculus on manifolds is to lift it from calculus on Euclidean space. Let's say Rm and Rn are Euclidean spaces, okay? So, and there's something else I should mention. If you have one local coordinate representative is smooth, well, good news, any other one is likewise smooth at P, because if you have overlapping charts, let's say U and U bar, and you have f of P is also in, correspondingly overlapping charts in N, V and V bar, then you can write the local coordinate representative with respect to the barred coordinate systems as the composition of transition functions, which we're assuming are smooth, and the local coordinate representative of the original function, which again is assumed smooth. So this is good news because it suffices to check smoothness with respect to a pair of compatible charts. If you happen to have 10 pairs of compatible charts at a point, all you got to do is check one pair and you're done. So that also implies things like if you check a property over an atlas, then it will then imply that that property typically extends to the maximal atlas over that atlas. So depending on the kind of argument you're making, it may be more or less practical to work with an atlas versus a maximal atlas. It really kind of depends on the direction of the question you're looking at. But anyway, so here we have a manifold, and here's the real line. And we're looking at a real valued function on the manifold. That's often a special case we're looking at. So in this context, we can define the derivative of such a function with respect to the chart on the manifold. How do we do it? We define it in terms of the derivative of the, basically a representative of the function from, Rm to R. And so this is an ordinary garden variety calculus 3 style partial derivative on Euclidean space, and this f composed with x inverse is basically the function represented in the Euclidean space. What is it, Benjamin?
I saw more of them.
You saw more of what?
Those crazy videos.
More crazy videos?
Yes, and one of them are going like this. Like he was on the ground, like trying to find out, but it's very going to be very funny.
Really? Oh, that's you'll have to show me later. Okay, thank you.
Yeah, I saw two.
Okay. So, sorry guys. The idea is that differentiation on M is implemented via derivatives of the local coordinate representative of the given function, but R has a global coordinate chart, so you only need to look at basically you only you only have to look at the coordinate chart on M. We don't end up with the, if you go back, what I'm referencing here is on the past page when we study, smoothness of the function from M to N, both the coordinate chart on N and the coordinate chart on M get involved here, right? But, I haven't defined how to take the partial derivative of a map like this in this lecture because it's not an issue, and we'll come back to that when we need to, if we need to, okay? There's always more calculus on manifolds to talk about, but so this y was not present because when n is equal to r, we can just use y equal to the identity map, and so there's a global coordinate chart of the identity map in this context. What is it, Benjamin?
Now we saw the creature and animal underground.
Underground. Oh, okay. Wow. This is very exciting. I don't know. I might have to go watch YouTube. And he's watching these primitive tool channels. I don't know what this guy's doing, but anyway. So here is an example of a function from the manifold of 2 by 2 matrices to the reals, and I'm just going to use it the determinant map. All right. So here's your global chart on our 2 by 2. It's a vector. Any vector space has a global coordinate chart. All right. So anyway, here it is, and the inverse of the chart is this patch right here. So x inverse of u1, u2, u3, u4 is u1, u2, u3, u4, And if I look at the local coordinate representative of the determinant, I get this lovely expression here, u1, u4 minus u2, u3. I partial differentiate that with respect to x with u1 if I'm differentiating with respect to x1. And so I differentiate that, I got u4, and lo and behold, evaluate that at my x of p as instructed up here, and out pops a22. So there you go. That is the derivative. How this, kind of wackadoodle looking formula actually is implemented. It's just a, you just have to kind of follow it step by step and do it. But really, when you just take a step back and look at what you did, if you didn't know anything about these formal definitions that I'm making, you probably would have calculated the same thing. Did I have that here? Well, I mean, what I'm trying to say is if I had written the formula for the determinant in terms of these, and then I said like partial differentiate with respect to x1 meaning a11, you would have found the same thing, like if you didn't go through all of this. I'm going through all of this just to try to make this formula less, ethereal. Moving on. So, next up we should talk about the tangent space, alright? So we can imagine the tangent space at M as a flat space which approximates M near P. However, because M is abstract and the visualization fails, we instead take a formal approach where the tangent space at P to M is a set of derivations. So if you study these things carefully, there are at least 4 sort of logically separate ways to formalize the tangent space. You can use equivalence classes of curves, like my picture kind of indicates, and you can define a vector space structure on the equivalence classes of curves, where 2 curves are equivalent if their derivatives are matching at the point in question, and we assume that all the curves are parameterized such that the the 0 parameter corresponds to the point on the path. So you can do that. You can also take it to be sets of symbols which transform contravariantly, and you can meaningfully define the tangent vectors like that. Or you can take this approach and define the tangent space to be the set of derivations, which is just a fancy word for derivatives, or derivative operators really at P. So the derivative operators at P act on smooth functions near P, and a derivation, it has to be a linear operator, which also satisfies the Leibniz rule. Of course, the coordinate derivatives, partial xi, are quintessential derivations, and in fact, you can prove that they form a basis for the tangent space to P at M. That is not obvious. That is something that you can derive carefully. Here we need, to prove that carefully, you do need that you're working on a smooth manifold. Only for a smooth manifold is the set of derivations finite dimensional at a point. If I recall correctly, if you're working over like a CP manifold, you lose this perspective, you lose this formalism, technically speaking. I think these things are in Conlon's. If I remember right, I studied a proof in Conlon's, C-O-N-L-O-N, if I remember right, Conlon. And I forget the title of the book, but he's got a lot of different books, but this one was like, his manifold book. Maybe it's called Differential Geometry. I don't remember. I had a student work through it once. It's pretty dense, but it's a good book. Okay, so I do think that like John Lee's books are more appropriate for students, especially self-study. There's just a lot more. I think the Conlon book is great, but it's kind of more. I think it's harder to get to details from Conlon's book, but Conlon's book does give a big picture more efficiently, let's say, perhaps. But I mean, there are benefits to every book. But okay, anyway, if you got 2 compatible charts at P, then the coordinate derivatives are related by the chain rule. So we can go from partial x to partial x bar. So I like this notation of using bars for the other coordinates, but as we're going to go on here and get back into Carol's text after this, for sure he's not going to use this bar notation, right? He's going to put like primes on indices to denote another choice of coordinates, yeah? So we'll run up against that. Just know that I like to put a bar over things to draw your attention. That's a different coordinate system, you know, whereas he likes to put primes on indices because that is what physicists do. And so here's the, if you had a vector, you can compare the components with respect to the coordinate system and the barred coordinate systems. And it turns out, if you look at it here, right, if we take that vector and, oh man, I think that's a, that's just, I was going to white that out. My bad. Let me just scribble it out here for now. I guess I need to rescan this again. Oh man. Oh well. I will try to send you the PDF of these, even though I'm hopefully making 2 videos here soonish. And well, anyway, Audric, I will send you the PDF here hopefully soon. Okay, so of these, although the PDF will not have a scribble, obviously, because I scan it at school. I digress. Let's get back to business here. So I take my vector field, I act on, let's see, how do I do this? What I'm doing is I'm putting the chain rule, I'm using the chain rule to substitute out partial xi for this right here, right? So I'm trading this for all that, yeah? And I pulled the sum over j out front. And then I said, okay, well that's also going to be equal to the sum over v bar k, partial x bar k, and then if what I can do is I can let both of these expressions act on, let's say, x bar alpha, and when I do that, that gives me a Kronecker delta j alpha here, and that gives me a Kronecker delta alpha k over here, which collapses the sum down to just v bar alpha and collapses this down to the sum over I of vi partial x bar alpha partial xi. So this is how the coordinates of a tangent vector transform. This is a quote-unquote contravariant transformation rule, right? So there's that. Let us move along. So coordinates on manifolds resemble calculus on Rn. You know, even if you have no idea what you're doing, if you know calculus 3 deeply and carefully, you can go a long way in this before somebody stops and says, do you know what you're doing? I mean, because pretty much calculus resembles the regular calculus. That's the genius of calculus on manifolds, is it's constructed in such a way that it really is, at least symbolically, identical to calculus 3. In as much as you can stay in one coordinate system and calculate, it's pretty much regular calculus. But to prove those things requires tracking through the chart and its inverse, and being a little bit pedantic and mathematical and such. And I think some of that is in the appendices to Carol. I am speculating, though I haven't carefully combed through those yet. Anyway, I probably should. The coordinates on manifolds often resemble coordinates on Rn. For example, if you take the partial derivative of Cartesian variable I with respect to Cartesian variable uj, you get Kronecker delta ij. So guys, I'm using u1, u2, un, let's say, for coordinates on Rn. And I'm generically using x's for manifold chart coordinates, all right? Also, there is a chain rule here, like that, and there's a chain rule here, like that. What this says, by the way, is that the Jacobian matrix of one coordinate transformation is the inverse of the Jacobian matrix of the other coordinate transformation, and that's still true for a manifold. Like you can, well, anyway, we have these rules, let's just say for now. So a vector field Next up, we should talk about vector fields. All right, moving along. Really moving along here. What is a vector field? A vector field on a manifold is just like a vector field on, subset of R3. It's a smooth assignment of a vector at each tangent space, P and M. That would be a smooth vector field on M. And the set of all vector fields on M is denoted, I usually read that, I don't remember what that thing is, but here's the set of all, we just call it chi. I don't think that's actually chi, but I have forgotten the name of that thing. Anyway, there's a set of all vector fields on M. So if you've got a vector field on M, that means that at any point P, you evaluate the vector at that point P, you get a tangent vector at P. And if you got a smooth function, and you let the vector field act pointwise on that smooth function, well, that defines itself, that gives you back a smooth function on M. All right, so in other words, more to the point here, smoothness of vector fields is judged by when you operate on a smooth function, do you get back a smooth function? If that's true for arbitrary appropriate smooth functions, you got a smooth vector field. So we can judge smoothness in that sense. All right. And yet again, that is the descendant of like a really careful analytical argument where you define smoothness in a more abstract way, and that's a derived consequence of it. In the same way that saying, a function from Rm to Rn is smooth if the Jacobian matrix has smooth partials. Okay, well that's a theorem. That's a theorem that is descending from a more primitive and natural definition of smooth maps of higher Euclidean spaces, and then a consequence of that would be that the Jacobian matrix is smooth. It's a sufficient condition that the matrix of the Jacobian be smooth, but it's not a necessary one, I don't believe. Well, I should be careful. It's in the case of differentiable functions, certainly continuous differentiability of the partial derivatives is a sufficient condition for differentiability, but it is not a necessary one. It is possible to have functions which are once differentiable and yet are not continuously differentiable. So anyway, enough about stuff we don't care about, sorry. So let's see here. So we may also consider vector fields along a subset of a manifold. For example, if you have a curve, right, a path, you can talk about the tangent vector field as follows. So like gamma prime of t, you differentiate the components of the curve and point it in the xi direction at the point. Here's kind of a picture of it, what's going on down here. All right, here's a picture. Picture. So you got your path up on the manifold. You take your chart, you project it down basically to a path in Euclidean space, and then you calculate the derivative in the ordinary sense here, and you take those components and you put them on the you stick them in the direction of the coordinate derivations up on the tangent space, and that's how you define the tangent vector field. And obligatory comment, this all collapses down to the ordinary calculus 3 directional tangent vector field to a path when you let the manifold be R3 and you just use the global identity coordinate chart. That's one of the things that points to the fact that these constructions are reasonable, is they do reduce to the ordinary calculus in 3 dimensions when you do it. All right. Now here's an example. If here's a vector field x partial x minus y squared partial y, that's a vector field on R3, and I can calculate, acting on the x function, I get back x. See, because when x hits partial x, it gives me 1. When x hits partial y, it gives me 0. So I just get x, which is just x again. When I hit the vector field here on y squared, y on partial x is 0, but y on partial y is just 1. So we just get back that minus y squared. And partial z is just 0. So what you can see from this is really the components of the vector field can be obtained by acting on the coordinate chart components, yeah? So like the x component is x, the y component is minus y squared, and guess what? There's no z component. So perhaps this calculation is a little bit instructive in terms of how you can find components from a vector for a vector field if you have the chart, you know. Anyway, here's another one just for fun. If we let v act on x squared plus y squared, we get so I differentiate x squared, it gives me 2x, so I get 2x squared. I differentiate y squared, it gives me 2y, so I get minus 2y cubed, like that. And so what this means is it can be understood in terms of directional derivatives, essentially. You know, if I study a particular point, right? For example, you know, plug in 1, 1. Look at what does this calculation mean at 1, 1? If we look at 1, 1, this gives me what? At 1, 1, this gives me, oh, it gives me 0. Oh, this isn't going to be helpful, that instructive. So that gives me 0. And at 1, 1, what's the vector field? It's 1 partial, so it's like partial x minus partial y, right? So what that means is that if you look at the level curves of x squared plus y squared at 1, 1, right, then in this partial x minus partial y direction, actually that's kind of interesting. All right, you know what? It is actually a little bit interesting. So at the point 1, 1, fine, I'll write it out. So here's the point 1, 1. What does v at 1, 1 look like? V at 1, 1 is partial x minus partial y. So that would be something like, attempt it in this, well, here we go. So that's basically this one, okay? There you go. That is v of 1, 1 in the usual low-tech way of drawing vectors, all right? It's going 1 unit over an x, and it goes minus partial y direction. So if you just identify partial x with, like, you know, the x unit vector and partial y with the y unit vector, it's like this, right? And when you plug in 1, 1 into this, you get 0. What does that mean? It means that if you look at the x squared plus y squared function, right, which, by the way, here's the level curves of x squared plus y squared. I drew the one, you know, level curves of x squared plus y squared are what? They're circles, you know, around the origin. Anyway, this derivative working out, the derivative acting on this function being 0 when I plug in the point 1, 1, it speaks to the fact that at 1, 1, that function, x squared plus y squared, it's not changing in the direction of v, right? Because v is actually a tangent to that level curve, and in that direction, the level is not changing. It's staying at level 2, actually, right? X squared plus y squared, 1 squared plus 1 squared is 2. If my vector field had a plus there instead of a minus, then I wouldn't have gotten 0. I would have gotten something more interesting, right? Which would have spoke to the fact that if the vector was pointing like this, you'd be leveling up for that level curve. So anyway, if you study these, you know, formal derivatives, they can be understood as directional derivatives. So like directional derivatives are tangent vectors is the way you can think about it. And I think Carol does a pretty good job of diving down into that and trying to understand it. But, you know, I would encourage you that you can, if you don't understand all of that exactly, you can still go on. It's like not that big a deal, really. All right, anyway, let me stop talking about what to not do. Next up, the cotangent space. So the cotangent space, TPM star, it's the set of linear forms. So you have mappings from the tangent space to the reals that are linear. This is known as the cotangent space, all right? And we can define the differential of a function such that it acts on vectors at a point to give a number. That gives you an example of a quote-unquote cotangent vector. So df acting on a vector field v is v of f. Now, if you fix a point here, if we say at the point P and let V be a vector at the point P, then, if you fix a point, then you'd actually have an element of TPM star, but this actually defines a cotangent vector field, the truth be told. But anyway, here's an example of that. If we study F, not of a cotangent vector field, I just want to expose this more. If we study F as the ith coordinate function, right? That's a mapping from U, which is a subset of the manifold, to R. And we do dxi acting on partial xj, then according to this definition, we do partial xj of xi. But hey, that's Kronecker delta ij. And what does this mean? Well, this means that, and I'm omitting the point, right? But this is, I'm really thinking about this all going on at a point. I have adorned the point down here so that you don't think this is pointless. Oh, I'm sorry. No, I regret nothing. I regret nothing. So there we go. This means that the dxi's and the partial xj's, these are dual. The dx's are the dual basis to the coordinate derivations. This is the dual basis to that. And as such, you can build an arbitrary type KL tensor. Yeah, you can build a type KL tensor from these dudes. So here's a tensor. And so if this is at a point, it's a tensor at the point. But if you let these be functions and you imagine, these ranging over a bunch of points, then this becomes a tensor field. And in particular, this is, the tensor product. And so we can look at a tensor at a point where we can assign a tensor to each point and thus produce a tensor field. I should mention that the coordinate derivation is identified with its double dual. What's that mean? That means that it can act on dual vectors. How does it do it? Like in the green down here. So like partial mu acting on dx alpha I, and this is a very silly definition, but here's what it is. The double dual of a vector makes a vector into an active object. How does it act on the one form? On the covector? It just lets the covector act on it. That's it. But so this is the canonical isomorphism of the double dual, and in practice. Again, my apologies if this is too quick. I'm really trying to, I'm trying to get to chapter 3 in Carroll as fast as I can, because that's where we're much closer to physics. And, whatever we don't understand about this, we're going to understand better in the context of doing the calculations in chapter 3 is my firmly held belief. Okay, so, all right, so anyway, bottom line here, if you let t act on these differentials and these partials, then when you sort through the definition of the tensor product and how it acts on this, k plus L tuple of things, it just produces a bunch of Kronecker deltas, and basically it selects the alpha 1 alpha k, beta 1 beta L component of the tensor. So if you want to select the components of the tensor, you simply act on it like that. Let it act like that. Which is kind of funny, because I just got done saying that to find the components of a vector field, we can just act on x. Huh. Well, but I guess it's just one more step. What's this? That is partial mu acting on x alpha I. So in some sense, it's really, all right, well, this is the kind of thing I must not chase. Let's go on. All right, so, yep. So sorry. Don't mean to tease you. Here we go. So next up, we talk about, in our whirlwind tour of calculus on manifolds, we'll talk about differential forms. Now, I'm not sure when we're going to actually need differential forms in here. I don't believe differential forms are actually used meaningfully in chapter 3, so this is maybe something we're going to come back to much later. But let me just put it out there while we're at it. A completely antisymmetric tensor is known as a differential form on an m-dimensional manifold. there are non-trivial differential forms of degrees 0 through m, which are referred to as p-forms. A 0 form is a function, a 1 form is a covector field, a 2 form is one of these guys. Notice that, here's the repeated index convention, and you can also I can make my sums explicit, so you either have less than or greater than for mu relative to nu. And then what I did was I relabeled this sum with swapping nu to mu, like that, right? And then I used the antisymmetry of this coefficient to flip that to minus beta mu nu, factored it out, like that. And then, by definition, this is dx mu, wedge dx nu. So you see I can rewrite the sum over all tensor products, right, as a sum over increasing indices of the wedge product. And so you have that, all right? So like with differential forms, it's sometimes useful to work over a basis. See, and if we're working in the context of antisymmetric tensors, the usual just dx mu tensor dx nu is not a basis, because you need for it to be a basis of the antisymmetric tensors, you need an antisymmetric tensor. And these guys form a basis, provided that you use mu less than nu, all right? So if you're interested in working with a basis rather than components, this is the way to go. If you're content to work with not a basis, but, you want to, keep sums over all indices, then you can work that way. I mean, it's just kind of a choice. But generically speaking, you can write a p-form like so. You zoom in a bit here, it's getting kind of tiny, isn't it? You can write a p-form like this, or you can write it as a sum over increasing multi-indices like that, where this dxi is a sneaky notation for this wedge, this wedge, this wedge, that. And that's a multi-index, yeah. And just to finish the story here right quickly, if you take the direct sum of all these different sets of p-forms, the 0 forms, the 1 forms, all the way out to the m forms, this gives you what's called the exterior algebra. And for the exterior algebra, if you take a p-form and a q-form and you wedge them, you get a p plus q form. And that p plus q form is related to the wedge the other way according to this rule right here. So they sort of commute sometimes, but anti-commute other times. It depends on the degrees, p and q, of the forms being wedged. And there's also a beautiful calculus here, which is known as the exterior calculus, where you take the exterior derivative of a form by simply taking the ordinary differential of the components of the form and wedging them with the differentials of the coordinates. That gives you a p plus 1 form. And it satisfies this graded Leibniz rule, as well as this often known as d squared equal to 0 rule. Watch what? Oh, very nice. Yes. Yes, I see you've got your balloon. Very, very nice. Careful, I don't want it to get popped on my thing, so you better take it back inside before you pop it, okay? Alright, moving on here. So there you go. There's differential forms in 2 minutes. Next up, let's talk about calculus tensor densities. Carol has a little bit to say about what's a tensor density. This might be a little bit more important for chapter 3 and forward, so let's just kind of sort through it here. So I'm going to say epsilon tilde is just the combinatorial epsilon symbol, which I usually just call the Levi-Civita symbol, although maybe that's at odds with the typical use of Levi-Civita in GR. I don't know. We'll see. But anyway, epsilon tilde is just -1, 1, or 0, depending on whether you got an even permutation, an odd permutation, or any repeat, right? He says it's a symbol and not a tensor. It's a non-tensorial object, according to Carroll. However, if we transform it as if it was a tensor, then a determinant appears. All right, so he's like, in other words, this is an identity, all right? It's like, I don't know. So like, what does this even mean? You're transforming, it's not a tensor, but we're going to transform it as a tensor. You read this kind of sentence and it just makes you go, what are you saying? Why didn't you just say, This is an identity which is true because the formula for the determinants, I mean, this is a formula which is true. Here's how I define the determinant in terms of the epsilon tilde. It's just the sum over, completely anti-symmetrized sum over the columns of the matrix is that's the determinant. And of course the determinant of the identity matrix is 1. Great. So if you look at this and you tilt your head and squint, you can see that this identity above is going to follow, you know, from what's below. You notice there's a difference. Yeah, I've got 1, 2, da 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 n. He's got mu1 prime, mu1 2 prime, mu n prime, and these are summed over, right? But if you think through this, the only time this term is non-zero, well, there's many times, but one time it's non-zero is when mu1, mu2, da da da, mu n is literally 1, 2, da 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 n. If that's the case, then that's going to make this 1, 2, da 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 n, right? And on the other side of things, that's going to be epsilon 1, 2, da 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 n, right? But the thing is, you could move that, well, I'm sorry guys, this is, you think about it for a little bit, this clearly implies that, but I guess to really prove it, I guess it might take a little bit of convincing students. I don't know. It's got the same anti-symmetry, like, you know, how can I say this? Part of it is, like, if this is 1, you can just move it to the other side, you know? If this is -1, you can just move it to the other side. Like, multiplication by 1 or -1 on one side becomes you can just divide it over to the other side and you still have the same thing. That's part of it. I'm going to shut up. I don't have anything constructive to tell you here, really, except that this equation 2.66, which Carol claims, I do believe is a straightforward consequence of my usual definition of the determinant. I'll just say that, all right? And so I said I can see how 2.66 follows from the definition above. And then next, Carol looks at the matrix, which is formed by...
Dad, I can't find the remote. I left it in the...
You did not bring the remote out here. It's probably in the living room. You better go back and find it, buddy, okay? So...
I left it right on the...
I'm sorry. I can't help you right now. I'm making this video. All right, so where were we? If we calculate the determinant, right, of the Jacobian of the transition function, that's what this is, I think, then let's see here. All right, so notice what's going on here is that this, I mean, if you just look at the equation 2.66, it seems like this should be on the other side, but notice carefully that if m is this, notice that's not m, right? That's the determinant of, this is actually the inverse matrix of m. And that goes back to something I told you earlier. This right here says that this and that as matrices are inverses, right? So that comes up here in that when I flip the mu prime and the mu, that's actually the determinant of the inverse matrix. So, but then the other thing is linear algebra, right? The determinant of m inverse is, by the way, 1 over the determinant of m. So if we were just to use equation 2.66, we'd have determinant of m over here, but then he solved it for epsilon tilde and put 1 over m on the other side, which is just written as the determinant of m inverse. All right? And anyway, here you go. So this right here says that the epsilon tilde symbol does not transform as a tensor, right? This, if it was just all this, it would be transforming as a tensor like we want, right? There's just the contraction over the indices with the other coordinate indices appearing. There's this extra determinant term out front, which is all kind of weird. And that what that by definition means is that, in fact, the Levi-Civita symbol is a tensor density of weight 1. The weight 1 means there's determinate first power coming out here. All right? So the way I would, by the way, just, notational caveat here, I might denote this by writing this instead, like epsilon bars, say epsilon in the other coordinate system is the determinant of partial x bar, rather than using the primes. I use the, oh, wait a minute. Did I mess that up? Oh, man. See, I meant to put the bar up here, obviously, right? The other coordinate system. So I really should have the bar up there, and that one I need to scribble out, okay? Sorry about that. I'll get with it eventually here. That's the pattern. The prime is upstairs, then prime is downstairs. So if I use the bar notation rather than the primed indice notation, it looks more like this. Okay. I'm getting tired. Let's move on. So, we'll discuss metrics, the metric more in more entirety, and we spent about a whole hour just talking about the metric next time, all right? But for now, just know that the metric is a tensor of this type. It's something like G, which is G mu nu, dx mu, tensor dx nu. It's assumed that it's completely symmetric, but anyway, let's just kind of sort through how that goes. So here, I really just want to talk about the fact that the determinant of the matrix of the metric is not a tensor, okay? Let's sort through that then. So if we think about this, we can form a matrix from the components of the metric. Basically, we think of that as the row index, that as the column index, all right? And this is the tensor transformation law of the metric, which when I look at it in terms of the corresponding matrix calculation, if I call this P mu alpha, that makes this, notice that the bar is downstairs, so the alpha goes to here, but the beta goes to there, which means it's transpose of the, anyway, that's the transpose matrix beta nu, G alpha beta, and so if I rewrite that, I've got P mu alpha, G alpha beta, P transpose beta nu, which, dropping the indices and just writing it as a matrix multiplication, is the transformed matrix is equal to P, G, P transpose, all right? And so if I take the determinant of the transformed matrix, I get the determinant of this product, but the determinant of the product is a product of the determinants, and the determinant of the transpose of the matrix is the determinant of the matrix. Consequently, we get that the determinant of P is squared and times the determinant of G, but P is this, and P inverse is that. So Carol writes this as follows. He just points out this, like the determinant in the prime system is, this is the determinant of the transition function, the determinant of the Jacobian of the coordinate transformation, the change of coordinate map. Ugh. Anyway, this is the determinant, and that's to the minus 2 power. So this means that the determinant is the determinant of a metric is a tensor density of weight minus 2. And we can use G to make epsilon tilde an honest tensor. See, because the epsilon, so this is how the G transforms, which means you can compensate the, you can fix the transformation law we had for the combinatorial Levi-Civita symbol by just adorning it with a square root of the absolute value of the determinant of the matrix, like so. So the Levi-Civita tensor, notice the lack of the tilde here, epsilon mu 1 mu 2 da 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 mu n is the square root of the absolute value of the determinant of the matrix of the metric times the combinatorial Levi-Civita symbol, where again epsilon tilde is essentially just the sign of that permutation, and with the understanding that when any index is repeated, the sign is 0. Otherwise, it's plus or minus 1, like we talked about. this is the determinant of the matrix of the metric, and of course the metric is that. All right, and so likewise you can define epsilon with the upper indices like so, and here epsilon tilde is defined to be the sine of g times epsilon lower tilde. What's the sine of g? Well, the sine of g is the sine of the determinant of the metric, which is a different use of sine than this sine up here was sine of permutation. This is the sine of the determinant of the metric. Oh, fun fact. If you contract two of these here epsilon symbols, you get this lovely anti-symmetrized product of Kronecker deltas. Here S is the number of negative eigenvalues of your metric. We have taken S equals to 1 in our standard nomenclature because we work with the Minkowski metric. We're going to be working with, well, more on that in the next lecture. We have S equals to 1 typically. If you want Riemannian geometry, take S equal to 0. So in Riemannian metric, all of the eigenvalues are positive, which makes the metric quote-unquote positive definite. Positive definite. All right, I've mentioned all of this primarily just to include the following comment, which is probably a throwaway comment for now, which is that if you have a p-form, you can define the Hodge dual to be an n minus p form by using, essentially by using the, by raising the indices on the Levi-Civita symbol, not symbol, but the Levi-Civita, good grief, words. This defines the Hodge dual. You use the epsilon symbol to raise the indices. Well, you raise some of the indices on the Levi-Civita symbol and contract those with the given differential p form, and that leaves you with n minus p antisymmetric indices, which are, in fact, the appropriate pattern to have for this n minus p form we call the Hodge dual. And it's also, it's not quite involutive, but it's kind of something like that. It's plus or minus that, because the Hodge dual of the Hodge dual is just minus 1 to this factor times the thing you started with. So anyway, if you want to see more on the Hodge dual, if you watch my Calculus 3 lectures at the very tail end of a lot of semesters, I do have a fairly decent presentation of the Hodge dual as it is concretely realized in 3 dimensions. But there's much more to learn about the Hodge dual, and oh man, what's the name of that? Bleecker. I think I may be spelling this wrong, but Bleecker, it's like it's on gauge theory. Maybe I want to say gauge theory and variational principles, but I'm not actually. If you look into here, it has the Hodge dual in more abstraction if you want to read it on it more deeply, and that's a Dover book. Anyway, so finally, conclusion, integration. So I've been talking about differentiation a fair amount. To do integration, we can only integrate an n form over an n-dimensional space, and to do it properly, you use this invariant volume tensor. So the invariant volume tensor is so defined. It is the square root of the absolute value of the determinant of the metric times d, dx0 wedge dx1 dot wedge dxn, and that actually works out to just epsilon, like the completely anti-symmetrized contraction of the coordinate differentials tensored. But keep in mind that this is not the combinatorial epsilon symbol. This is the one that's got the metric dependence hidden, packed in it. All right. And so anyway, to calculate the integral of a scalar field over a manifold, you simply integrate the scalar field multiplied by the invariant volume tensor, and that's how you define the integral. Now, I don't know when and if we're ever actually going to use integration on manifolds in this course. I don't recall ever integrating on a manifold in my general relativity course, except perhaps to define an action very late in the course. So, hey, if we get to that, that'd be awesome. So anyway, hey, that's it for now. Thanks, guys.